I'm Shobhana Narasimhan. I'm a professor in the Theoretical Sciences Unit at the Jawaharlal Nehru Centre for Advanced Scientific Research. I've had 2 CEFIPRA grants so far with the same group. It was first the group of Sylvie Rousset at the Université de Paris Diderot in Paris. And the second grant was also with her. But then in the middle of the grant period, she moved on to another job, a senior administrative position. And so I continued to work with other people in the same group, Vincent Repin and Jérôme Legoutte. And we have just concluded the second grant also. And they've been very successful. Okay, so our first project was on what are called nanostructured surface alloys. So alloys are materials made of more than one metal mixed together. So for example, brass is an alloy of copper and zinc, and bronze is an alloy of copper and tin. These were known from ancient times, but not all metals can be mixed together to form alloys. So for example, iron and gold don't mix together to form an alloy. And the new discovery in this field about a decade or more ago was that though they don't form three-dimensional alloys, certain combinations of metals can form a two-dimensional alloy. That is a layer of alloy which is just one atomic layer thin. And the goal of our project was to discover new such materials. And this was a joint experimental and theoretical project. So the French group is an experimental group and our group is a theoretical group. And it really went back and forth between the experiment and the theory. So first, the experimental group, that is the French group, wanted us to identify two metals that they could work with, which would form such a two-dimensional alloy, even though they don't form a three-dimensional alloy. And our goal as theoreticians was to predict which combination of metals would do this. And so we found in our project, once we started working together, that if you take iron and gold and deposit it on a surface of a metal called ruthenium, such an alloy is likely to form. Then they did the experiment in the French group, and it was really nice. It actually worked. I mean, as a theoretician, you make predictions all the time, but it's very exciting when somebody does the experiment and it actually works, and they did it and it worked. But then they found that the atoms arrange in some particular way. Okay, every gold atom is surrounded by 6 iron atoms, or the other way around also, every iron atom is surrounded by 6 gold atoms. So the question is, why does that happen? Why do you have that particular arrangement? And then we were able to go back and do further calculations and understand that if an iron atom is surrounded by 6 gold atoms, it is able to have a very high magnetic moment, and this reduces the energy of the system, and this is why this material forms. So this was the big success of this project. This was published in the journal Physical Review Letters, which is a very prestigious journal in the field. It was also covered by the popular science art magazine New Scientist. So this was our first project. Our second project was sort of similar in spirit, but we were focusing more on the magnetism. And we're not just working on two-dimensional materials, but we're working partly on two-dimensional materials and partly on molecules deposited on two-dimensional materials. And this is broadly motivated by the field of spintronics, which is this idea that you have a new kind of electronics where what you're exploiting is not just the electron's charge, but also the electron spin. And we've been working in this broad area of molecules on surfaces. We've had all kinds of exciting discoveries. For example, the French group found that if you put what is called a spin crossover molecule on a gold substrate, it arranges in a ordered fashion where you have an alternation between high spin and low spin states. And our calculations could explain why this happens. There's also a two-dimensional material called phosphorine. It's a single layer of phosphorus atoms. And if you stack it a few layers thick, then you get what is called phosphorus, of course, but you get certain kinds of phosphorus, like black phosphorus or blue phosphorus, white phosphorus, etc. So we were studying black phosphorus, and the French group found that black phosphorus has certain defects. Defects are where the perfect arrangement of the atoms is spoiled and something goes wrong. You may have a missing atom, you may have, instead of a phosphorus atom, something else called a substitutional defect, etc. Now, what they do in the French group is they do something called scanning tunneling microscopy. It's a kind of microscope where usually people say you can see individual atoms, but what you actually see is not the individual atoms. It's as if you see a signature of how the atoms are arranged. So you see the signature, and from that signature you want to know what is actually going on, how are the atoms arranged. And to interpret those signatures is a little bit difficult to do it purely experimentally. And that's where the theory, the calculations that our group does come in. So we can try different kinds of arrangements in our calculations and calculate what would be the signature that these arrangements would produce in the experiments. And from such a calculation, we can tell the experimentalists, this arrangement, this defect is what you are seeing in your experiments. So it's really a very close collaboration between experiment and theory. And we also found in the case of phosphorine that the experimental group, the French group, was able to change the arrangement of atoms by giving a pulse of electricity, sort of giving a little boost of energy to that area with the scanning tunneling microscope tip. And our calculations could show that when you do that, you go from something that's not magnetic to something that's magnetic. This is a prediction. And now, again, we have told the experimentalists this, and they will try to study the magnetic properties. So it's really going back and forth between experiment and theory. And we've had some very exciting findings. They have resulted in very good publications. We have publications together in some very prestigious journals, and we're really very happy. Okay, so I had been aware of Sylvie Rousset's group and her work, and she had been aware of my work. We were studying very similar topics, but her group was doing it experimentally, and our group was doing it theoretically. So it was a natural fit. It was very natural for us to collaborate, but I doubt that we would have actually started collaborating as intensely, as intensively as we did if it weren't for CEFIPRA. CEFIPRA forced us to think about what is it that we could really do together, how can we combine our strengths, and then write up a proposal, and then start working together, start exchanging students, start exchanging visits. We found, once we started writing the proposal, one funny thing that we realized was that Sylvie, the French PI, is exactly 1 day younger than me. And so we both now, of course, every year on successive days, we celebrate our birthdays and always remember to wish each other. And because we're exactly the same age, our career stages are very similar. Our worldview, I would say, is very similar. I think one very important thing about the CEFIPRA project is the exchange visits, because, of course, we do communicate by email. We used to have Skype meetings, we have Zoom meetings, and all of this, of course, has become even more common after the pandemic set in. But we've all come to realize that there is nothing like meeting in person. Even if you are having regular Zoom or Skype meetings, there is something special about sitting together side by side and looking at the data and having discussions that go on all day, sometimes very late into the evening, which really stimulates the thought processes, makes the science leap forward. We have found again and again that our research is, of course, progressing along, but every time the French group visited us or we visited the French group, there was a big leap forward. The big advances came when we made one of these exchange visits. And so that, I think, is a very important part of the CEFIPRA formulation, these exchange visits. Also, the French group have had 2 PhD students from India who were funded by CEFIPRA, and I think that has been a very nice part of it. Those students have really been absorbed well within the group, became very much integrated into the group, into French culture. One of the students had actually done his master's in JNC, so he knew us very well and then went and joined the French group. I also think there are lots of intangibles that you get as a result of the CEFIPRA grant and the exchange visits. For example, many of my students have accompanied me on visits to Paris, and many of the scientists and students in the French group have come and visited Bangalore. And we have really shared not just the science, but the cultures of each other's countries. And this shared experience really tightens the bonds, strengthens the bonds, bonds of friendship, but those strengthening the bonds of friendship also strengthen the scientific collaboration, I think.
Long live India and France friendship.